Good afternoon, everyone. I'm happy to welcome and introduce Professor Brian Johnson as our guest speaker at the Welsh School of Architecture, Cardiff University. Brian is an associate professor emeritus at the University of Washington. He is an academic researcher and teacher interested in the intersection of design, the built environment, and digital computation. That means design cognition, physical and ubiquitous computing, digital design and analysis tools, collaboration and communication tools, human-computer interaction for design, digital representation of the built environment, digital fabrication, and as he puts it, various other nooks and crannies. He is the author of many research papers and a book titled Design Computing, an Overview of an Emergent Field, published by Routledge in 2016. From 1987 to 2013, Professor Johnson served the Association for Computer-Aided Design, Acadia, in architecture, Acadia, as its webmaster, member of its steering committee, and president. Acadia is where I met him and where I followed in his footsteps, also serving on its steering committee and leading it for a couple of years. Over the years, Brian and I became friends, and in 2013, he graciously accepted to write the afterword for my book, Parametric Design for Architecture. Brian is a self-deprecating person, but don't let that fool you. His insight into and long experience with design computing is unparalleled. He can offer the long view and untangle the current issues through deep analysis of the patterns that he can detect where others cannot. Brian, welcome again, and thank you for sharing your thoughts on design computing with us.
Thank you. Okay, well, let me say that I'm glad to be here, and I will share my screen. Let's see if I can get the right subset. And I'll begin by observing that if you've been using Google to try and find out anything about me, I'm not that one. Once upon a time, you could find me near the top of the Alta Vista search engine, but not anymore. There are too many Brian Johnsons in the world. What I want to talk about today is not the most current trends, because frankly, I've been sort of out of the mainstream for the last couple of years, having retired just as the crest of COVID swept over the United States. But I want to talk about the cover that I chose for the book that Wassim mentioned. This book is intended to be an introductory text for people who are interested in design computing, but don't have a deep technical background necessarily. It's more concerned with some of those big ideas. So I thought it might be appropriate to talk about why I picked an image, and I picked it, that represented a sort of old-fashioned clockwork mechanism as somehow an appropriate image for a book about design computing. And that's what I'm going to talk about primarily. And then if I don't burn through all my time, I'm going to move on to talk about some of the ideas that are on the inside of the book as well. Along the way, I'm going to lean on a number of other references that I have found particularly meaningful over the last couple decades. And one of those is the book Metaphors We Live By Lakoff and Johnson, no relation, which explores the common metaphors we find in advertising, in signage, and in everyday language that relate concepts that would otherwise seem disconnected together into useful patterns. These often show up in user interface design issues as well as straight up design circumstances. And one of the principal metaphors that we're familiar with in the context of design, which is represented here by a piece of art, the worm Ouroboros, is the design cycle, the notion of a process that consumes itself and grows through that process of repeated cyclic pattern. And let me then start, as part of looking at that, with another book, Herb Simon's The Sciences of the Artificial, where he declares that everyone designs who devises courses of action aimed at changing existing situations into preferred ones. I like to use really simple setups for some kinds of exercises. So this is a problem that I had at one point. That's my study, and there's a hat sitting on the shelf. And the problem was I wanted to get the hat back. Now, if the hat were sitting on the printer in the foreground, I could simply reach down and pick it up. That's just action. Is that a design act at all? It just requires that I have a body and that I know how to use it to some extent. On the other hand, if I've recognized this situation before because I store the hat there regularly, then I may know that the walking stick that's leaning against the artwork there can be used to reach up under the hat brim and lift the hat down. That's a function of experience. And then finally, I may recognize, having used sticks in other settings, that the walking stick is available and could be used in that way. So I may have an analog condition that I can extend to that. Design progresses through often a variety of levels of expertise. And as we become more mature designers, we begin to acquire more things which we might think of as memory access rather than imagination or a creative action. And all of the things that we do in the process of design sort of fall into this spectrum of expertise and need to be accommodated within that. One of the other touch points for thinking about this is this idea that we often see in design context, that we take the main idea of the design and we divide it up into parts that we can cope with. So if we need to do a bridge design, we need to do the towers, we need to do the suspension cables, we need to do the bridge deck, and we do each of those things as a kind of separate design process that we weave together in the end, following this kind of divide and conquer strategy, which is often presented as a straightforward linear process of understanding the problem, brainstorming solutions, coming up with the strategy, and then executing the solution. That linear model, while attractive in some ways and occasionally appropriate, is not the cycle that we see most often presented for architectural design contexts and many others, primarily because of two problems or awarenesses that we've come to. One of those is wickedness, and the other I've labeled here as jazz. We'll get to that. Horst Riddle and Weber in 1973 published a paper in which they identified wicked problems, and this term stuck. While they worked out of a planning context, they described a variety of ailments that many designs have where they cannot be readily assessed or implemented without causing some kind of difficulty for the designers and for the people that have to live with them. And so they characterized design problems in particular as wicked problems because of that. And many architectural problems in particular, because buildings tend to be one-off kinds of constructions, are of this nature. So wicked problems suggest that the linear model is going to have problems, going to have difficulties. Lucy Suchman, in her PhD research for that she did at Xerox was looking at why it was that operators of these very large copiers had trouble interpreting and executing the instructions that were printed on the copiers for unjamming them. And in that process, she ended up comparing the sort of divide and conquer planning logic from Western cultures with the navigational model used by the Pacific Islander peoples, which was much more of an improvisation, a more jazz-like navigation strategy for getting from one point to another, and brought that insight back into understanding things about human-computer interaction. These collectively then began to make an understanding about design and design problems as one of approaching the understanding of the problem itself and the understanding of the solution simultaneously. And several authors have written about this more recently, but the term puzzle making, which Archaea coined in 1987, is one which I find particularly attractive, that we use process to get to the solution. It's not through some sort of creative insight necessarily. It's not through some kind of intuition. And then we end up with looking at design as a process of cycles. Donald Schoen, in his Reflective Practitioner series of books, identified a number of professional practices where the experts converse with the situation, where they reflect in action and try different kinds of things and test it against an understanding that is perhaps not one that can be made explicit through words, and yet it produces a desirable outcome. And this model of design cycle then is the one that we most often see in some form or another, the sort of generate, test, and refine, big categories, then broken down perhaps into steps along the way that can be executed. We'll come back to this a couple times more as we go forward here. When you put that design cycle in the context of time, we then end up with some sort of a spiral which converges gradually on the desired product or finished design through a process of eliminating the unknowns or the uncertainty over time. Don Norman, who's written a number of books, or had this particular book, The Design of Everyday Things, reissued through a number of editions, took the concept of affordances from Gibson and applied it to objects in the real world. And architecturally, if you've ever run into one of those glass facades at street level where you're supposed to push through the glass and you're not sure which side of the door to push on, you've run into an affordance problem. If you have a push plate on the door, it's very clear where you're supposed to, how you're supposed to interact with that. That is from this idea of affordances. And this commonly shows up now in discussions about human-centered design and human-computer interaction. He was working principally in the space of product design, so prototyping and testing were an important component to this as a way of understanding how it is that people actually interact with the objects that we do make. And the teapot on the cover is indicative our understanding of what we can do with this particular object and how it's supposed to be used. Okay, so if we try to take this into an understanding about computing, this is a vastly oversimplified kind of view of computing, but we start out with things in the real world that we somehow squish into the computer through a variety of input devices, keyboards, cameras, mice, etc., that do stuff to the information in question. So if we're measuring distance with the digitizer has a resolution. The digitizer may have an axis alignment that forces coordinates to be in some kind of particular relationship and so on. All of that happens as a process during input to create data that lives inside the computer. That data is then manipulated by algorithms which make other or more data. And then eventually we do something with that, whether it's as simple as storing it as a text file of numbers or letters, or we turn it into instructions to a CNC machine that then cuts it out of a sheet of plywood or steel. And the CNC machine itself will add output artifacts to the final thing, depending on the step size of the head and the cutter or the laser or whatever it is that's doing the cutting. All of those things become then parts of the artifact. And we see that really easily in the context of images, where we get photos that capture an image at a certain resolution, although these days it's high enough that we often don't realize the raster. The output then to printer or something like that also comes with a particular resolution, both in color space and physical space, and those things affect what we get out. So the data, when it's on the inside, has certain characteristics, and the algorithms have certain characteristics that we need to look at as well. While we don't see the innards of computers quite like we might have once, where they were blinking lights and so on, it is still true that within the machine, discounting quantum computing, the values, the information is represented by collections of bits. These little collections can be clumped together into groups, most common one being, of course, byte, that the groups can then be manipulated as representing something. So memory becomes available as a place to put information if we can encode it. Because memory is organized in a particular way, it's particularly easy to encode binary integers, but they're still basically an interpretation. We stick information into memory. If you've ever had the experience of opening an image file from a format that your software no longer supports or doesn't know what to do with, you will get some sort of an image, but it will be gobbledygook. It will be unrecognizable in terms of what it was supposed to be, because the interpretation has become impossible. So it's important that both sides of encoding and decoding are supported by the tools we use. It's also important in Charles Babbage's analytical engine, there was a separate separation of program from actual computational engine. But the modern computer stores the code which describes the algorithms that are executed on the data in the same bits that it stores the data in. And this means that hackers have an opportunity to overflow array boundaries and shove executable code into places that it's not supposed to be. And it also, of course, means that programmers have an opportunity to create bugs that do many of the same things. That's indicative of that mutability within that, but it's important for us to remember that that representations are created by shoving information into the representation, which gives it certain characteristics, and then interpreting data out of the representation at some point in the future in order to accomplish something. All right, and we'll come to that. And then, of course, programming. If you've learned any kind of a programming language, all the way from assembly to Grasshopper, you've worked with a set of basic mathematics, a process of shoving results into bits of memory, playing by the rules of a particular variable or type, and then coming up with logic actions that do things like branch and cycle on bits of data, chunks of data, to make it more efficient. And all of this is what we now put together into our large assemblies that do things like machine learning, and that are built out of hundreds of thousands of lines of this very simple kind of organized thought. It makes them seem magical, and in fact, sometimes they act in ways that surprise us, but it doesn't mean that they aren't comprehensible. And that's one of the truths that I've been aware of in terms of thinking about computing in the design context over time. So clockworks and code have certain similarities. They're made out of simple components, whether it's simple operations in the case of the computer, or simple shapes in the case of the clockworks. There are things that we can inspect and we can interpret. This has become one of the problems in machine learning because often we don't see very clearly what happens on the layers between input and output. And they become the foundation for very complex assemblies, including the 10 millennium clock. It's intriguing that both clocks and computers are often described in terms of their improvement life cycle. Clocks drifting 50% less every 30 years or so, and Moore's law indicating chip density, and often interpreted as compute speed, doubles every couple of years. So there are these kinds of similarities, and we can then legitimately ask whether computer, represented here by Babbage's analytical engine, is executed more recently, a modern creation that in his time it was not possible to fabricate all of the parts at the machining level that was needed, or the glockenspiel on the left. They're really closely related, and yet one's a clock and one's a computer. So I come to this and think, often we present computers as sort of quasi-magical. We look at the results that they can produce in terms of rendering or modeling, and they're phenomenally complex things, but they're built out of simple parts, and they're not magical. And I wanted the cover to emphasize this notion that we can understand them, we can potentially assemble new collections of parts to accomplish something that is new. We may or may not be able to actually accomplish everything we can conceive of, because it still takes time for the parts to execute. But we do end up with some understandings that we can glean from one to the other. And in particular, this notion that that it's not magic, it's orchestrated thought, that we may have a wand, but the wand is used to guide and organize, not to focus some sort of magical operation. So that's why I picked the image. I think I liked it. It represents my understanding of computing and its accessibility in part, because magic is something you're either born with or you're not, whereas being able to peer into the insides of a clock and work out how it works requires a modest understanding of basic physics and some time and attention. And I think designers and all the rest of us have the opportunity to understand computing and its application in design without resorting to intimations of magical operations. So that's the first part of the presentation that I wanted to make. The second part is to actually look inside the cover a little bit and talk more about design computing writ large. I see it as this intersection of three parts, design and computing, obviously, but in the context of the built environment, because we need to take into account that wickedness and that improvisational process of conversing with the design problem as part of addressing what we're doing with the technology. It's also the case that digital infrastructure is now becoming part of the built environment in the sense that we include everything from cable chases to machine rooms into buildings, but also in the sense that we occupy buildings. We do security systems, we do energy systems built around computational models, and those change how we use them. And then we insert humans into buildings still, and those humans act in ways that may or may not be consistent with the models that we've built up for how people should occupy buildings. But we can use computing to fine-tune our buildings in terms of things like energy performance and cost control. We can use rendering software to produce very precise understandings of how buildings will look, both on the inside and the outside. And then we have something like COVID come along and it sends us all home, and it turns out we don't need buildings. So how do we understand how technology potentially changes the way we use buildings? Do we need buildings with classrooms anymore if everybody's going to watch this on YouTube from their dorm or their home? Those questions also become part of the general environment of design computing. The promise of digital applications within the domain of design can be traced back to this kind of an understanding that in the process of design, you make decisions, the decisions become harder and harder to change without severe repercussions because we build decisions on top of other decisions. And that means that if we could sort of build a hierarchy of decision making that says do the important stuff first, we could probably save time. We could probably save missteps and make our buildings and our designs better. So the desire is to use computing to front load the decision making in a sense with intelligent decisions so that we cut the overall cost, we cut the potentially the number of missteps that we make and so on. And in doing so, we achieve increased profitability because, of course, design happens in the context of a firm that's trying to make money. So people began looking at the design cycle and saying, well, there's this that goes on. There are opportunities to improve our survey of imagery related to design ideation. There are part libraries to improve the speed with which we can construct representations. There are advanced simulators that will do energy and lighting and other kinds of simulations for us once we set up the data. And so on. And these kinds of opportunities then become part of the way we have approached, often piecemeal, using the computer. And we shouldn't understate the role of collaboration, coordination, and communication as one of the opportunities, because a design is not produced by a single person most of the time. There may be a lead designer who's responsible for major decisions, but it's still accomplished as a collective action, and orchestrating that collection and common activity is one of the challenges. However, it turns out if you compare the construction industry with other non-farm industries and look at the application of digital tools to these various industries, the non-farm industries have seen increasing productivity over the last 60, 70 years, whereas construction has not. And one of the remaining questions, still persistent questions, is why is this and what can be done about it, if anything? And you get firms like Katera that come along that say, well, what we need to do is just apply a completely different model of construction and design to the industry in order to bring that curve up, lift that tail of the curve. That hasn't worked out so far. So there remain questions at the level of thinking about the industry as well as questions at the level of thinking about bits in a design representation that are worth engaging in. And I concocted a short list of what I think of as the design challenges. Wassim and I have exchanged some email over the years trying to identify particular grand challenges in design computing. There are various lists that can be concocted. These come out of what I put into my book, and the three that are highlighted in yellow are three that I built some slides to talk about a little bit today, if I don't run out of time, which I'm likely to do here. So representation is probably the biggest one in some senses, although it's different. Representation has various fundamental challenges. If we look at something like Corbu's sketches for Rorschach, they start out very simple, very wiggly, very evocative, but not very detailed. They grow much more detailed, and eventually we, of course, end up with a building. The sketches are all done with ink on paper, which remains one of the most flexible means of capturing and developing a design representation. but they aren't the design as such. The design existed as a composite of all of those things. But it is a challenge to bring together the various modes of representation, the various ways we have of thinking about representations, and putting them into a single unified kind of model. One of the other significant challenges in this context is that the information that a HVAC engineer needs and uses is fundamentally different from what a structural engineer needs and uses, is different from a lighting perspective, is different from a the architectural visualization perspective. So these different purposes often require or encourage the production of different kinds of models, as well as differences in scale. The difference between a facade as seen by a designer, where it's a multi-story storefront facade, versus what the contractor needs, which is a floor-to-floor sliced up version, so that they can build that as a series of things as each floor progresses from construction, during construction. These are just different ways of understanding the same thing, but they are different. And whether we can support those differences or not becomes a bit of a challenge. I was shocked at a BIM conference I went to a number of years ago that there was routine acceptance of the notion of 3 BIM models. There was the design BIM, there was a construction BIM, which was built by the contractor in order in part to test the construction process they were foreseeing. And then there was the operational BIM that was built by the owner or for the owner to make use of. All of these things are things that concepts like digital twin, right? Metaphors like digital twin suggest we can get rid of. Well, we may not be able to because of the way people use these things. And if we can't get rid of the multiplicity, maybe we have to figure out how to accommodate it. I've always liked this particular graphic, that different people see projects in different ways. And we have to keep that in mind. We also have these problems of what I call emergence and expertise, in the sense that at one point in the design process, because it is a cycle, we create one representation, the 2 squares on the left, and then at some point we say, oh goodness, that's a potential courtyard or a potential central tower or something else. And so we want to reinterpret a previous representation into a new one. We're often stuck with the process of editing to get to that now, whereas we'd like to get there somehow more readily. I'll skip expertise for the moment. We'll move on to look at the challenge, not of representations, but of solutions. The person who defines the problem often ends up constraining the solution, both intentionally and unintentionally, because they characterize the problem in one way. We need a new building. Well, maybe you don't. Maybe you need something else. Maybe you need to use an existing building differently. But the way you characterize the problem tends to have a lot to say about the solution. In order to come up with a finished solution, you need to have a means of generating candidates. It's not always clear how to do that. You certainly don't want to do it random. You don't want to have upside down bathrooms in the, in parts of the building. You need to generate candidate solutions in a way that's useful. We often hear about, I want the best possible solution, which always makes me sort of prick up my ears, because of the traveling salesman problem, which you may be familiar with, but given the 16 dots on the right, there's perhaps one path through them that is the shortest path that connects all of them, which would be what the salesman would like to do. There's a really straightforward algorithm for finding that path. You produce a list of all possible paths and their distances, and you pick the short one. The problem with that is there's 21 trillion alternative paths through those 16 dots. And yes, current computational tools can wade through those 21 trillion alternatives fairly quickly these days. But every time you add a city, it goes up by a significant number because the number of alternatives, if you're going to test all of them, depends on n factorial. And that number gets really big, really fast. So exhaustive enumeration is not a really useful strategy, even though it's easy to define. So solutions and finding solutions and testing solutions becomes one of the interesting challenges. And of course, somewhere along the way, somebody always raises the question of whether they, where's the creativity? Where is the designer in all this? If you're picking a solution out of a pattern book, is it good enough? And we'll leave that for now. One more point, the practice challenge. Again, design exists within a context, and that context is a commercial context. In the United States in particular, the industry is a very fragmented industry. Each project is formed out of a client, obviously, various potential designers, consultants, contractors, subcontractors, and actual tradespeople that do the work. And this is a very fluid and fast changing kind of picture, which means that it's really hard to get certainty that you know what's going to happen based on what you as the designer is doing. So you want to control what goes on, but you have limited tools for doing that. Government has a hand in trying to control what goes on as well through codes and through taxes and through keeping records of what's been built for fire safety protection and so on. And all of these things make for a model of activity which is very, very cumbersome to change. Changes implemented by well-meaning clients for the purpose of gaining more data about their buildings, perhaps, can have very negative impacts on the construction process because the contractors weren't anticipating doing it in that particular way, and so on. So these remain challenges. So I'll wrap up with this idea that ideas take a while to catch on. That's first mouse prototype done in 1964. That's my current mouse, done in 2000 and something. It took about 20 years, and it's often the case that that technology changes take about 20 years to have their full impact. So clockwork, yes, but change happens in spite of that, and even clocks change slowly, and we can see that in the fact that the time does move on. The AEC ecosystem, as I now see it, I think has been plagued by the fact that our approaches to problems have been as fragmented as the design cycle's various steps and as the industry itself, and that it remains to be seen how it takes place. But what we really need is in a sense, a new axle, a new way of anchoring that cycle so that it goes around a single driving action that moves the design forward. So that's a little longer than my 40 minutes that I was allocated, but we'll call that a wrap. I will put this one last slide up just for yucks, illustrating some of the changes and roughly parallel developments within the AEC universe. We shouldn't be surprised that it takes time for stuff to happen. But there's also this synergy between technology changes in one part of the universe, one part of the ecosystem, and reverberations, let's call it, in other places. So what blockchain does to us ultimately remains to be seen, but we will probably see some various kinds of things. Thank you very much.
Thank you, Brian. As always, very, very insightful and a really good look back at the fundamentals of what we do. I think that is quite important. If I'm just looking at the participants, you know, to let them know that they can put questions here, or you can, if you are in the room, you want to raise your hand and ask a question, I'll ask you to come over so that the mic can pick up your voice. Otherwise, if you are online, you can ask a question online in either in the Q&A or in the chat. I'll pick it up. But to give you a little bit of time to collect your thoughts, I will start with a general question. I've been at this for 35 years, not to date myself. Brian, you've been at it a bit longer, probably. So we've had an opportunity for the 20 years to take effect. Is there, have you seen, for example, a positive development that we were talking about when we were doing our masters or starting our PhDs or doing any kind of research, that has taken hold in a positive way? And is there something that you can identify that is probably by now close to getting implemented, if it started about 10 years ago, that it will have another 10 years? What are some of the patterns that you see are starting to become mainstream?
Sure. Well, one of those I would say is in your work with manifold and non-manifold representations, because there is we begin to understand how our spatial senses are linked to our representational models in a way that's more manipulable and more usefully calculable. I think also that the development of visual programming models of one sort or another, such as Grasshopper and generative components, which offer the opportunity for the designer to engage the problem. It's a little bit like the very beginning of that very last slide, the advent of Fortran enabled people who had understandings about computation, calculation, let's call it, to begin to take calculation and put it into a digital context in the form of those early programs that did everything from floor plan layouts, which were nice because they were associative graph models, but they didn't take much real estate in memory. And memory was expensive, and right. So there's this ecosystem relationship between the what things we can conceive, it's a bit of an affordances argument, and the tools which developed out of that. And now that we've got GPUs that can do real-time processing of high-end renderings, we get that, but we begin to have tools that can build complex computational models around the geometry models. And that's an invitation to do all the kinds of things that we see people doing with Grasshopper and tools like that. And so those are positives. I would like to see a re-emergence of more of attention to some stuff that was done in the 80s and 90s with capturing design rationale, because I think that the process of keeping track of why, if you look at the notion of practice and then the model of what goes on in an office, all too often, the way you know why we did something is you go and ask Mary or you go and ask John, because that knowledge lives in somebody's head, and it shouldn't. It should live somewhere in the design model. And so I think it's there are opportunities that our abundance of disk space and memory have that we may begin to use, although I've heard of BIM models that are just amazingly big. So there's clearly some, I think one of the words I put in my advert text for this talk was compost. And compost is my way of tagging the idea of condensed knowledge, of taking all the fluff somehow and getting just the nutrient core, the good stuff that is important to the next cycle. And we don't know how to make compost yet.
Yeah. I remember. I mean, I'm intrigued by the idea of capturing design intent. It's something that thought about for a long time. In terms, I was in the camp of saying the artifact itself can somehow encode and capture design intent, but I think actually that's not quite enough at this point. I remember when I was a junior architect designing a facade, and I designed the facade. They left me to design it, and then the more senior architects came and they said, "Oh yeah, great job, but let's change it in this way or that way." And I was like, "Why are we changing it?" Well, that's how we do these facades. Like that is the language that we are expecting, and the head principal architect is expecting. So they had that kind of innate knowledge that they only knew as almost like a secret club, that they know what is needed, and that's not encoded explicitly anywhere.
Right. It's selected. It's in that category of memory, right? It's something that, and there's a great story. I mean, one of the problems in representation, there was a firm in Seattle, go nameless, that maintained past projects online in a digital archive so that they could access it. Totally reasonable. And they had this problem where this particular project had a roof detail that was not good. Well, this roof detail keeps showing up on subsequent projects, because when somebody wants a roof detail, the most likely way to do it is to go and select it. But there wasn't a mechanism for management of the firm's understanding. That's a compost problem, right? And so we're stuck with sort of project by project layers that don't interact with each other.
Yeah. Let me go quickly. Oh, this is not an actual. Just will you post the recording? Okay, so that is not a question. Yes, we will post the recording. Are there any questions from the room? No, I think yeah.
Are their eyes open? It's always important.
Well, yes. Yeah. This is my group.
Hello.
Right. I think, I mean, I think we'll end it here then, because I know it's getting late. It's getting to 5 o'clock. I think people need to get home. But thank you very much again, Brian, for your talk, and we'll catch up soon.
My pleasure. If any of your students have questions they'd like to drop on me by email, feel free to share my email address with them. I'll try to respond. And good luck with the rest of your day.
Thank you. Thanks
December.
Thanks. Bye-bye.
Bye.